Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Jean-Luc Margot with us today. Hello, Jean-Luc.
Hi, Frank. Thank you for having me.
Well, thank you for agreeing to talk about your very interesting paper, which we're going to get to here in a moment or two. And you have this lovely blue ball behind you as your background. And where is your geolocation on that big blue ball?
I'm on the west coast of the United States. I live in Santa Monica, California.
Santa Monica. All right. Excellent. Excellent. Let's see. And it is September 2nd, 2024 as we record this. And so it's actually probably a pretty nice time in Santa Monica in September and October. June gloom is over, yeah?
It's pretty much always a nice time in Santa Monica, California.
I biked through there once. It was an interesting experience, I have to say. Very cool. Very cool. And Jean-Luc, what do you like to do for research?
I'm a planetary astronomer. I'm interested primarily in the dynamics, spin states of planets and satellites and asteroids. That's
Cool.
what I do for my primary research. And about a quarter of my research is also devoted to SETI.
Ah, okay. Very cool. That's a nice combo there. Very good. And that is going to bring us to this very awesome Planetary Science Journal article. It is open access. It's the open access era, people. Go grab a copy for free. Quantitative criteria for defining planets. Jean-Luc, take us away.
Thank you. Well, first, I'd like to acknowledge my co-authors. It's been a pleasure to work with them. Brett Gladman is a professor at University of British Columbia, and he's previously worked on planetary nomenclature. So he was a logical and a very good co-author to have. And then Tony Yang, who is a high school student, actually, who approached me to do research having to do with machine learning and astronomy, and I thought about a project that might be suitable of the right scope. And so we ended up doing unsupervised clustering with Tony, and he did an excellent job on this paper. So it's been a thrill to work with both of them.
That's awesome. That's quite a dynamic range there. Let's put it that way. Very cool. Okay, let's go.
So the motivation for the paper is that we have a definition of the term planet at the moment that we feel is inadequate. I was at the 2006 meeting, the General Assembly of the IAU, where this definition was discussed and voted on. And it was probably the best that could be done given the odd circumstances under which the definition emerged.
Yeah.
However, it remains inadequate. And we feel it's inadequate because, first of all, it excludes exoplanets from the definition, right? So the first clause there is that it says a planet must orbit the sun, and we obviously don't want to be limited to solar system bodies.
Indeed.
The second issue that we have is that the definition remains quite vague, ambiguous. Clauses B talks about assuming hydrostatic equilibrium nearly round. It doesn't say how round. How do you measure that?
Yeah.
And clause C talks about cleared the neighborhood, but again, it doesn't quantify to what extent, the size of the clearing, the time scale for the it just says has cleared. If an asteroid enters into a planet crossing orbit, does that make the planet no longer a planet? It's generated a lot of confusion and a lot of ambiguity. And we felt that as a community, we really ought to do better, right? As scientists, it's our job to define terms precisely, unambiguously. And so we made this attempt. These are just proposals, and we're hoping to encourage community conversations about how we can improve the definition of planet.
Good. I'm with you.
All right. And then another motivation for the paper is related to a recent working definition by IAU Commission F2 exoplanets in the solar system. And they had a working group tasked with coming up with a working definition for an exoplanet. And so they came up with a working definition. It includes a few new elements compared to IAU resolution B5 from 2006. So first of all, they introduced an upper limit of 13 Jupiter masses.
Right. Your turn, Vernon.
They expanded the scope, so to include stars, brown dwarfs, and stellar remnants, which makes a lot of sense. And then they include something about a mass ratio that we'll get into in greater detail later.
Cool.
And it concludes by saying the minimum mass or size required for an extrasolar object to be considered a planet should be the same as that used in our solar system.
Right.
And that's all very good, except that we do not have a precise definition of what that is in the solar system. And so we're sort of left with an ambiguous situation again.
Okay. How do
Right.
we
So in this paper, what we tried to do is try to provide a framework for defining both planets and exoplanets. We think we can do both in a single unified framework. And we have a proposal that is very much aligned with everything that the IAU has proposed to date.
Okay.
And whether we want to keep all of these elements or not is up to debate, I think.
Yeah.
And then because there are quirks, I will say, with some of these clauses, we also have a second proposal, which is a purely mass-based criterion.
Okay.
Now, we're not particularly in favor of the mass-based criterion. Our team feels that having physical principles to guide the definition is something useful.
Yes.
And so that's our primary philosophy, essentially, is to use physical principles to establish meaningful thresholds, and then we're going to adhere to those thresholds for the purposes of defining objects.
Cool. Very cool. Okay. Got it.
So in section 2, which may seem a little bit out of place, but we need dynamical dominance in the next section. So in section 2, we introduced the concept of dynamical dominance. And this is fairly important because, as we know, Ceres, Pallas, and other asteroids were at some point considered planet, but then when we discovered that they were not dynamically dominant, we essentially said, well, no, they're not planets. And they lost their planetary status, essentially, at that time.
Yes.
Something similar happened to Pluto, right? In 2006, what really changed the status of Pluto is the fact that it's not dynamically dominant. And so we felt it was important to describe what dynamical dominance is.
Yeah.
Now, I should say, the status of Pluto has changed, its classification has changed, but nothing has changed about how exciting and scientifically interesting Pluto is, right?
Absolutely.
So, I want to be very clear about that.
Absolutely.
Here, we're just in the business of developing a classification system to help us think about formation issues, to help us communicate the science, and so on and so forth.
Cool. Okay.
So in 2015, I wrote a paper to describe dynamical dominance. And at the time, we had not included brown dwarfs as part of the potential bodies around which, a celestial body could be considered a planet.
Right.
And therefore, at the time, I used the main sequence lifetime of a star as a logical time scale to define over which time scale the clearing must be done.
Okay.
Now, that will no longer work for brown dwarfs, and that's in part the reason why we have this updated paper with an updated time scale for the clearing.
Okay. Okay.
So we want to quantify what it takes for a body to clear its neighborhood.
Okay.
And we wanted to define the extent of that neighborhood. So there's a well-known concept in planet formation studies, which is the feeding zone of a body, which is the range and space where a growing protoplanet can accrete material.
Okay.
And so we thought that region would be a logical definition of a zone to be cleared. And it turns out that can be defined as a function of the Hill radius, which is also a fairly well-known quantity. That's equation 1.
Yep.
And the canonical feeding zone is 2 square root of 3 times the Hill radius. So that's well defined. It's also easily measurable because it depends on the mass of the celestial body, depends on the mass of the central star. Both of these can be typically measured fairly easily, and it depends on the semi-major axis, which can also be measured fairly easily.
Yes, timing.
So that was important to us, right? It was to define, to propose a definition that is based on concepts that we can easily observe and measure.
Good, good. Okay.
So to clear a zone, we followed Tremaine, who wrote a nice paper in 1993 about what it takes to clear a zone. And it's essentially modeled as a diffusion process over a certain extent, over a certain clearing timescale. If you want more details, you can read the 2015 paper, but we arrive at equation 2, essentially, which tells you what is the mass that it takes to clear that zone, that feeding zone, over a given time scale.
Okay.
Right? And so again, everything there is pretty easily measurable. The only arbitrary choice in this equation is the choice of the clearing time scale.
Correct. Yes.
Right?
Yes.
So again, in 2015, we used the main sequence lifetime of a star. In this paper, we're going to use something uniform for all stars, brown dwarfs, and stellar remnants. We're going to use either 10 billion years or the age of the universe, whichever. It doesn't make a big difference.
Sure. Okay. Good.
And then for any celestial body that you contemplate, you can attach a dynamical dominance ability, if you will, by taking the ratio of the mass of that object to the necessary clearing mass, right? And that's equation 3. It's a parameter pi. And we write down the expression for pi in equation 5. And again, it depends only on the mass of the body and the semi-major axis, right?
That's a good one right there. And there's mass clear.
Right.
And then you plug that back in, do a little rearrangement, and you get the planetary body. Okay, pi is 807 MA to -9.
Right. So if you want to see what that looks like, you could jump to figure 8.
Okay.
That shows the parameter pi in the solar system. It's in the appendix, right? So there it is. We have the mass on the vertical axis, and we have the semi-major axis on the horizontal axis. And the solid black line is pi equals 1, right? So anything above that line has the ability to clear its orbit in a 10 billion year time scale. Anything below the line does not have the ability to clear its orbit in a 10 billion time scale.
Okay, cool.
What sort of struck us and others in this particular metric is that there's an order of magnitude difference between the group at the top in green, the 8 planets, and all the other bodies in the solar system below. There's something like 3 orders of magnitude, right? Difference. That is notable. That is significant. That is something that nature has done that requires some explanation, right? It's a fundamental difference between these 2 classes of bodies. And so in our view, dynamical dominance is something that must be acknowledged and honored in a classification system.
Agreed.
So if we can go back to the dynamical dominance section.
Sure. Let's head back to where are we?
So,
sorry, there we go.
Right there. Yep. So that last paragraph on the left, this is an important difference between our proposal and the IAU definition. You may recall that the IAU definition talked about must have cleared its zone. That is very difficult to determine, right? If you want to determine whether an object has cleared its zone, essentially you need to do an inventory of all the bodies in that zone and decide whether it's cleared or not. And that is extremely difficult. You need to do a survey to very small sizes. We can't even do that in the solar system for exoplanets. Forget it, right? It's completely impractical.
And it's fuzzy still.
It's still fuzzy, right? So what we propose instead is an ability to clear a zone. Right? It's not an observable, really. It's, do you have enough mass And are you at a location where you can clear a zone of a specific extent, of a well-defined extent in a well-defined timescale?
Yes.
So
Good.
it's an ability that is observable in a sense, because we can measure the masses of the bodies involved and the semi-major axes, but it's not something that requires a survey of small bodies.
Yes. And this line cracks me up. There's a little philosophy there for you.
Um, all right. So the other advantage of having a definition based on an ability clear zone is that Jupiter, for instance,
Okay.
while it was still forming, had not yet cleared its zone.
Sure.
And therefore, according to the IA definition, an early type Jupiter would not be a planet.
Yes.
Whereas in our proposal, it has the ability to clear its zone, and therefore it is a planet.
Gotcha.
Likewise, if planets switch positions, as may have happened in the solar system, right? You might argue, well, then they clearly have not cleared their zone. But again, in our definition, as long as in our proposal, as long as they have sufficient mass, they have the ability to clear, and they retain their status as planets.
Cool. Looking good so far.
All right. So in section 3, we then thought about what sort of practical guidelines we would like to establish a planetary taxonomy. And so one of the concepts we want is that something that contributes to our scientific understanding of the population,
Yes.
does not obscure important aspects of the planetary system, right? That
Yes.
it highlights them. And also, we want a taxonomy that's based on something that is observable and measurable.
Yes.
We don't want a taxonomy based on something that cannot be observed, because that doesn't help us
much, right?
in classifying
Right.
objects.
Very pragmatic definition here.
That's right. So in that context, we thought about what can we measure when we discover a new planetary system, right? And the things we can measure, first of all, we measure the orbital periods, the semi-major axes, right? These are the first things we can measure. And then typically we can get estimates of masses, either directly or indirectly. If we can measure sizes, there's typically a size mass relationship that we can use, so that orbital parameters and masses are the things that we can most easily determine about newly discovered bodies. In that last paragraph there, we describe in contrast, the fact that the shape of a planetary body is not something that we can measure. And so
most of the time,
when we talk about having a practical or pragmatic definition, something that's based on the shape is essentially a non-starter, because even in the solar system, for instance, there are trans-Neptunian bodies that we've known about. There's satellites that we've known about for decades, and we still don't know what their shape is, despite best efforts, right? We mentioned a couple of examples there, Nereid and Orcus and Salacia. Essentially unknown. We've known about these objects for a long time, and we don't know if they're approximately round or not. And that problem is going to be magnified by orders of magnitude when we talk about exoplanet, exoworlds, essentially.
Yes.
We're not going to be able to measure their shapes anytime soon.
Right. And even if you could, there's still rotation. Like if you had a Jupiter or Saturn, it's not going to be spherical. So, yeah.
Right. So we talk a little bit about what you can do with stellar occultations, what you can do with light curves. These are both great techniques. We can learn about bodies, but we can't come up with a confident 3D representation of bodies, essentially short of a spacecraft flyby, right? And so we don't want a definition that requires a spacecraft flyby.
Good luck.
Right. All right, so in the next paragraph, we talked about the fact that taxonomy in general, in nature, not just astronomy, but biology and other fields, is usually done by looking at observable properties, looking at how things cluster,
Yes.
right, in the variety of phase space, and then assigning a class to the individual clusters, right? And what we noticed is that roundness, for instance, does not yield nicely separated clusters. And in figure 1, we showed the for the a large collection of some of the most massive bodies in the solar system, we showed what their status is in terms of roundness. Are they likely to be round, unlikely to be round? Is it uncertain? Is it close? Again, very difficult to establish for many of these bodies. And what we see is that there's no clear gap. There's no clear transition. There's, in fact, about a 2 orders of magnitude range in mass at which bodies are likely to become round.
Yes.
So not easy to draw a line there anywhere in that graph. The only line that we could sort of perhaps agree on is that anything that is above 10 to the 21 kilograms appears to be round, right? And so if you had to make a determination about the roundness of something and you didn't have the observations to determine whether it's round or not, you might agree that, okay, if its mass is above 10 to the 21, let's say that it's round.
Okay.
But, it's not particularly satisfying, but that's sort of the best we could come up with. All right. Right, so that mass, just to give you an example, corresponds roughly to the mass of Ceres or Dione, right?
Yes. Yes, here we go. 17, 17, 18. Yep. I'm with you.
Yeah. All right.
Certainly at 10 to 23. Yeah. Sure. Okay.
All right. So we're sort of abandoning roundness as a useful taxonomic tool, and we instead select the properties that are available to us. So we talked about orbits, orbital parameters, and we talked about masses. And so in the next section, section 4, we conducted this unsupervised clustering of solar system bodies, right? So we looked at the 35 most massive bodies in the solar system, again, trying to put ourselves in a position of, hey, we've discovered a new planetary system out there. What do we know about it? How can we classify these bodies?
Yes.
And we're going to just let an unsupervised algorithm look at how these bodies cluster according to various properties. One of the reasons we like the unsupervised clustering is that it completely removes the emotions out of this problem, right? We essentially consider these as data points, and it's even better if you don't have labels on the data points, right? Because you just let it fall where they fall. And then you say, okay, well, there's a cluster here and there's a cluster there. And then you figure out where Pluto is, right? Pluto is,
I was going to bring that up, yes.
really is best to try to disconnect any emotional attachment. And so we like the unsupervised clustering for that reason.
Yes. Good.
We used k-means clustering as our initial clustering tool, but the AAS statistics editors challenged us and said, "Hey, why don't you use other clustering algorithms?" And so we did, and it was a great addition to the paper. It didn't change the results, but it was a great addition. So
but that helps build in robustness to it, right? I tried 10 different mechanisms, and I all basically got the same answer. I mean, you just add robustness. So let's hear it for the peer review process at the PSJ. Yay.
All right, so k-means is the idea that you minimize the distance between the centroids and the body. So we provide the algorithm there. And then another interesting aspect is that when you do a k-means clustering, you sort of have to decide how many clusters you want. That's not something that we wanted to impose. And so there's a tool out there called the silhouette analysis that lets you lets you decide what the optimal number of clusters is, right? So that's a fairly well-known concept. And so it tells you whether a point is more likely to belong to the cluster to which it was assigned or to the nearest cluster. And then you do some sort of averaging of the silhouette scores, and it tells you, okay, in this data set, 2 clusters is the most logical number of clusters, or 3 or 4 or 5 or 6, right? So that's what the silhouette analysis does for you.
And that goes before the k-means clustering.
It's sort of,
or in parallel.
You run it in parallel, right? You run a k-means on 2 clusters, 3 clusters, 4 clusters, and then the silhouette tells you
how likely that is.
2 is the best number, right?
Okay, good. All right, I'm with you.
All right, so in 4.3, we start with, again, the first thing we can measure, which is semi-major axes, right? So we have these 35 most massive bodies in the solar system. We run them through the cluster analysis. And in figure 2 is what the result is, right? So there's one cluster in blue and one cluster in green.
Yes.
And it turns out, and perhaps not terrible surprise, that the green cluster is all the satellites, right? And the blue points are all the bodies orbiting the sun, right? So in this group of 35, we have all the planets, we have all the major satellites, we have the moon series, and we have 10 trans-Neptunian bodies, including Pluto and Charon.
Right? The other symbols are. Okay, gotcha.
And again, the clustering analysis found that there's 2 clusters in here. There's the satellites on one side and bodies orbiting the sun around on the other side.
Cool.
And that's, that's something that we felt good about, that there's a clear distinction between satellites and planets. This is a distinction that we've known about for, hundreds of years. And it's a distinction that also makes a huge difference. If you think about Europa or Io, orbiting Jupiter, and the way they look now, right?
Sure.
If you take the same bodies and put them in orbit around the sun at 5 AU, they would look nothing like what they look now.
Right. Is there very proximity to those gas giants, right?
That's right.
Like Io, right? Io wouldn't be Io if it wasn't next to Jupiter.
It's a fundamental aspect of their personality, if you will. And so we thought that the taxonomy really ought to honor that as well, right? Is it a planet? Is it a satellite? It makes a difference. So that's our first guiding principle for the taxonomy, is let's keep a distinction between satellite and planets.
Cool.
Then we clustered according to mass, which is sort of the second quantity that we can measure fairly easily. And figures 3 and 4 show the clustering according to mass. So now we've removed the satellites from the data set, and we're left with 18 of the most massive bodies.
Let's do 3 first.
And so interestingly, when we cluster according to mass, there is no strong preference with respect to 2 clusters or 3 clusters. They score almost identically, and they do something that, again, you might expect. So when it's 2 clusters, it says, okay, well, there's 8 planets and there's everybody else. And when it's 3 clusters, it says, well, there's the outer planets, the giant planets, there's the terrestrial planets, and there's everybody else. Right? So that's again, a fairly reasonable outcome of this unsupervised clustering that guides our thinking about how to classify bodies. And in the solar system, you can see that 10 to the 23 roughly is, is a reasonable dividing line between these 2 clusters. But in the spirit of the IUU definition, we then went further and we said, okay, well, let's now look at the combination of mass and semi-major axis. So let's look at dynamical dominance. And let's do the clustering on that. And that's shown in figure 5, I believe.
And there's going to be our finding there. Let's do figure 5, revised criteria. Figure 5, k-means clustering.
Right. So here's the clustering of these 18 bodies according to this dynamical dominance metric that we described in section 2.
Yes.
And in this case, the silhouette analysis is, there's just no question. There are 2 clusters here. Cool. And there's the 8 planets in one cluster and everybody else in another cluster, with, again, a gap of something like 3 orders of magnitude, which is really striking, right? Nature has created a planetary system that has a huge gap between these 2 classes of bodies.
Okay.
And that's something, again, that we feel is important to recognize in the nomenclature.
Yes.
And that led to our second proposed principle, which is dynamical dominance is just a natural organizing principle for planetary taxonomy.
Yep. Makes physical sense. Okay.
We feel good about that criterion as well, because if we think about protoplanets again, growing in the early solar system, right? There's the protoplanet that's going to become the Earth, and that one is successful at accreting, 10 to the 24 masses of kilograms of material. And then there's the other protoplanet near Earth that doesn't, right? And these 2 bodies have undergone vastly different evolutionary histories, right? The Earth has been able to accrete sufficient mass to hold on to an atmosphere, to differentiate, to create a magnetic field.
Nice.
Again, it's a very different body than the bodies that have not been able to accrete as much mass. And so it's another reason why we feel that dynamical dominance does matter in the end when you think about planetary evolution. And the other reason why we feel good about it is that we also expect a similar partitioning in exoworlds, right? So when people conduct simulations of the growth of protoplanets in a wide variety of settings, a number of works have come up with a small number of large dynamically dominant bodies emerge out of these simulations, right? And then you have the sea of small bodies that are left over. So we expect, although we haven't seen the sea of small bodies around exoworlds yet, right? We expect that at some point we will discover these similar small bodies. And so we hope that this is a distinction that is robust as well.
Yes, and we would be extremely surprised to find no smaller bodies. That would be a discovery in itself. Very cool. Okay.
All right.
Okay.
So, so to summarize, we have planets versus satellites, and then we have dynamically dominant bodies. We think those are 2 useful guiding principles. And now we need to, in section 5, we need to revise the criterion for dynamical dominance. Now, recall that in 2015, I had used the main sequence lifetime as the clearing timescale, but when we include brown dwarfs, that timescale does not exist, right? So we need something else. If we want to include brown dwarfs, and for stellar remnants, it's sort of ill-defined as well. So in this paper, we propose, let's just use a uniform common timescale for all bodies, stars, brown dwarfs, stellar remnants. And it doesn't really matter what that timescale is. We sort of favor 10 billion years because that's the main sequence lifetime of the sun, but you could pick 13.8 billion years, the age of the universe. It makes very little difference. We provide the expressions for both. And it makes no difference as to the classification of solar system bodies. And you'll notice in equation, let's say 10, for instance, right? So this is very similar to the equation that we had for the pi parameter for the sun. It just has this additional factor about the mass of the central body, right? So it's very easily generalizable to exoworlds. Everything else is the same. And with this criterion, we verified on figure 6 that all the confirmed exoplanets are indeed planets according to this criterion. So if you go to figure 6, it'll show you all the confirmed planets color-coded according to detection technique.
Cool.
The pi equals 1 line is the solid line at the bottom, right? So anything above that is dynamically dominant, right? It can clear its orbit in a 10 billion year time scale.
Yes.
And we find that everything we've discovered so far is, again, qualifies as a planet according to this criterion, including the pulsar planets.
Yeah, I was gonna say the first ones. Right here.
Now, of course, that doesn't mean that bodies around other stars, there are no smaller bodies around other stars. We just haven't discovered them yet, right?
Right. Very cool.
All right.
This is a nice shot. I love this plot.
Thank you. All right. So now we can get to the actual proposed definition that we submitted to the IAU. So that's in section 6. So based on everything that we've done. So again, our first proposal tries to incorporate as much of the IAU recommendations as possible with the generalization that we're proposing and the quantification that we're proposing.
Very good.
So it's going to be a bit of a mouthful for these reasons, but
that's okay.
Let's get started, right? So planet is a celestial body that orbits one or more stars, brown dwarfs, or stellar remnants.
Okay.
So that makes it more general. It follows the recommendations from the IAU working group. That one is pretty straightforward.
And accounts for binaries.
Right. In clause B, here's our proposal: a sufficient mass to dynamically dominate the neighborhood around its orbit. And as opposed to leaving it sort of vague and undefined, we provide a specific quantitative criterion, right?
Yep, fairly easy.
A mass larger than this, and then you qualify.
Cool. Okay. Okay, good. Yes.
Clause C is again a leftover from IAU resolution B5. It's this idea of hydrostatic equilibrium.
Yeah.
But since we can't measure the shape of bodies, we're proposing this addition of a quantitative criterion, which is a mass greater than 10 to the 21 kilograms.
Okay.
We're not super excited about this clause, but we think it's better to have an actual threshold than none at all.
No threshold, right?
And
sure.
Another reason why the community might want to argue about this clause is that it turns out that in almost all contexts, not all of them, but in almost all contexts, a mass that is sufficient, an object that has sufficient mass to dynamically dominate its neighborhood, is also round, right? So if you qualify with clause B, you're almost certain to meet clause C as well. Again, not always. The exceptions are bodies that are orbiting very low mass stars or brown dwarfs.
Yes.
In that case, it is possible for a body to be dynamically dominant without necessarily being round or meeting that 10 to the 21 kilogram.
Right. Good. Exceptions are good. We'll always have to have exceptions to rules. Very good.
In clause D, so this is straight out of the IAU working group, is the idea of having an upper mass limit. And I think most people are on board with having an upper mass limit. Whether people are on board with having 13 Jupiter masses as the upper mass limit, I think is probably half and half. But there it is. It's the recommendation from the working group.
Right.
And then clause E, which is the clause that we're least excited about, is this idea introduced by the working group that there has to be a mass ratio requirement to qualify as a planet. So essentially,
Okay.
the mass of the body cannot be more than 4% of the mass of the central body. Otherwise, it's not considered a planet according to this clause. Now,
Correct.
our team does not like it. Again, we've included here in the interest of trying to move the ball forward here. But this, for instance, would exclude
Yeah.
4 Jupiter mass planets around low mass stars.
Right.
The reasoning from the working group, I think, was that they wanted to introduce a distinction according to formation mechanism, right? So
Yeah.
they felt that, for instance, a 12 Jupiter mass object orbiting a 14 Jupiter mass object should not be considered a planet.
Binary.
But it has its issues, right?
Right.
If you limit it that way, you introduce other problems.
Correct. Okay.
And then we have a satellite as a celestial body that orbits a planet, right?
Mm.
So now that might require additional work, by the way, right? You might want to have a minimum mass on the satellite as well, right? So we didn't get into that, but I'm sure that people might want to have a minimum mass on the satellite as well.
Very cool. Very cool.
All
And
right.
discussion, and we're going to come to that in a minute here too.
Right.
Uh-huh.
So this is the proposal that we submitted to the IAU back in December. It did not
I was going to say
make.
we just had an IAU meeting.
That's right. That's right. So one of the reasons why the 2006 debacle happened is because the Planet Definition Committee disclosed its proposal at the meeting, right? Nobody knew about the contents of the definition prior to the meeting. It was disclosed in an embargoed press release, right? So the press found out about the definition before the astronomers did. As soon as the astronomers found out about it, they realized, well, there's flaws in this definition. We need to fix it. And then, over the time scale of the General Assembly, with a busy schedule of sessions and trying to fix a definition was very difficult. Again,
2-week, 3-week time scale, yeah.
We got to where we got.
Yep.
Probably was the best that could be done under these circumstances, but it's not a good way to do it, right?
Right.
So you want to release the proposals well in advance of the meeting so that the community can review them, criticize, provide feedback, and so on and so forth.
Absolutely. And
so that's
hopefully to some consensus, right?
Right. Well, yeah. Or at least something that people can be content with, right? Maybe not.
Fair enough.
Not everybody's going to be happy with a final definition, but at least something that people can live with or be content with.
And something people can calculate with.
Right.
Right? Otherwise, it's just words. And words, blah, blah, blah. Calculate it. Very good.
So that was our hope, let's submit it to the IU long before the meeting so they can publicize it, so we can get feedback. We would like to get the feedback from the community, how can we tweak it? How can we improve it? For whatever reason, that didn't happen. Instead, I was invited to give an 8-minute talk about the proposal at the meeting, and which I did. And that's as far as it's gone so far.
One step. It's one step.
It's a small step.
Yes.
The hope is that at the next IAU General Assembly, maybe that time an actual resolution will be put forward, and we'll see what, whether we can actually solve this problem that's been around for, almost 20 years now.
20 years now plus, yeah. All right, so very cool.
In section 7, we propose a simpler proposal, but frankly, we're not particularly keen on it. We don't think that the community is necessarily keen on it either. And this is the idea that the proposal is complex at the moment. And if you wanted something that is much simpler, you could, come up with something that is much simpler, you sort of abandoned
Yeah.
the connection to the physics in that case. You just draw lines in the
Draw
sand.
lines of mass and
And right. So it's less satisfying
yeah.
from that perspective. It's a little bit easier to describe and convey to the public, maybe. But
Yep.
so for that proposal, we kept clause A, orbits one or more stars, brown dwarfs, or stellar remnants. Clause B adopts the dynamical dominance division at 10 to the 23 kilograms, and clause C is the upper mass limit, right? So again, not particularly thrilled about it. Not sure that this is going to go anywhere, but we wanted an alternative just in case.
Yeah, no, right. And sometimes it's good just to throw up stuff you know is going to get shot down, leaving.
Well, no, that's
chaff.
that wasn't really the intent. So the intent is that we did recognize that there were quirks in our proposal. So I described those briefly on the left-hand side there. So dynamical dominance, right, is by far the cleanest criterion that we've identified, right? It honors this huge gap that nature has created for us. And yet some of our colleagues are not thrilled about dynamical dominance because dynamical dominance has a distance dependence, right?
Yes.
It takes more mass far away from a star to clear a zone than close to the star.
Sure, agreed.
And so some of our colleagues are a little bit uncomfortable with the idea that an object could be dynamically dominant close to a star, but not dynamically dominant far from the star. And therefore, it could have a different label.
True.
Right.
Okay.
Now, we are not particularly distressed about this because there's ample precedent in planetary nomenclature for having different labels as a function of context. So we mentioned the TNOs, right, that become centaurs, that become planets, right? It's the same object. It just has a different categorization depending on this context. And so as far as we're concerned, having an object that is a planet close to a star, but not necessarily a planet far away from the star, it's okay with us. Whether it's going to be okay with, again, the community is unclear. It's something that we'd love to get a better sense on.
Very cool.
The second aspect that is problematic with the definition is the shape-based aspects, right? We know we can't measure that, and reducing it to a mass threshold is the best you can do, but you could argue that's really not great either, because there's going to be objects on either side of that boundary. You know, you're going to have objects that are less than 10 to the 21 that are perfectly round. They're going to be excluded, right? There's going to be potentially objects larger than 10 to the 21 that are not particularly round.
Right.
So it's imperfect in that sense. And then again, this mass ratio issue, which is probably the most disputed of all, is that something that's greater than 4% of the mass of the central body cannot be a planet. I think there's a lot of opposition to that. So
okay. Well,
so that's why we came up with this alternative proposal. But again, we're not particularly thrilled about it. What we're hoping is that the community gives us feedback, helps us improve the definitions of the proposal so that we can come up with something that we could vote on in 2027 and finally have precise definitions for these important astrophysical terms, right? Absolutely. What is a planet? What is a satellite?
Absolutely. Very cool. Very cool.
Oh yes, I should mention we do have an appendix, a couple of appendices. One is some details about the clustering algorithm scores.
Yep.
And Appendix B is the actual resolution that we propose to the IAU. It differs in slight vocabulary and the order of the clauses, and it differs in slight detail, in small details, but it's the section 6 proposal essentially.
Cool. Very cool.
Thank you.
Jean-Luc, I want to thank you so much for walking us through your thought-provoking article. Very nice. Very nice. Very good. Let's see. And you touched on it a little bit there on this current proposal under discussion, and maybe something will happen by 2027. And I don't know, so let me just ask and push on it a little bit. Are there other proposals out there besides the ones you have put up? Are there 3 or 4 different competing proposals, or are they roughly the same, differing in details? And just sort of, aside from putting it out there, getting the discussion and having a vote eventually,
Right.
where is the state of the other proposals, and where do we go from here?
I'm not aware of another proposal that's been
Okay.
submitted to the IAU.
Okay.
There is a group of planetary scientists who are particularly distressed that Pluto is no longer a planet, and they've been working hard on coming up with a definition such that Pluto remains a planet. And they're, emphasize the roundness aspects, right? So that's their idea, is that anything that's round is a planet, and planets, satellites, doesn't matter, they're all planets, right?
Got
So
it.
that's sort of their alternative proposal. We dislike it for a couple of reasons. One, again, this planet-satellite distinction is pretty fundamental,
Yeah.
and we don't want to obscure that. And second of all, roundness, again, is not something that we can measure. So we don't like it. I don't think it's particularly interesting. We do think that having a word for bodies that are round is something that is worth thinking about, right?
Yeah.
And such words have been proposed. So Gibo Basri has proposed to call planetary mass objects planemos, anything that has sufficient mass to turn itself into a sphere, right?
Yeah. Mm-hmm.
You can think about other worlds, right? A circumworld,
Yeah.
a sphero. You could come up with a name that honors the category of bodies that have pulled themselves into a round shape. We just don't think that to classify exoworlds, it's a particularly useful criterion.
Yeah, fair enough. Well, I'm also glad you're really looking at, beyond the solar system, right? Which is a little smaller in 2006. It's big business now. So is there a venue where people can weigh in? Or is that strictly done through some formal IAU? I mean, to get, is there some website people go to and, type in their comments, or, how do people get feedback on this?
Yeah, great question. So we actually created a survey to get a sense of the community position on this. And we sent it to the IAU asking them, could you please either conduct it yourself or circulate it for us? And they haven't done that so far.
Okay.
So we managed to get some responses from IAU General Assembly attendees this year through the Slack channels. We publicized it there. And so we have some sense of where the community stands, but it would be very nice to have sort of an IAU-wide survey. Hey, here's a proposal. Here are the clauses. How do you feel about each clause? And are you on board? Are you not on board? It would be extremely useful.
Have that discussion.
To know, right? And how would you improve it? And we think that would put us in a much stronger position in 2027 to have a proposal that the community has already weighed in on.
Mm-hmm.
We already know what's likely to be accepted, what's likely to be, frowned upon.
Yeah.
And then we could, move forward and look better as a community, right? That
Absolutely.
we are organized. We have come up with a definition that our community is supportive of, and we're going to have a vote, and a strongly positive vote, right? That's really what you want.
Yes, that's really what you want. And the way you get that, of course, is by doing what you just said. Have those discussions up front, right? Let people hash it out. Well, very cool. Well, I really look forward to having those discussions. So let's that's kind of why we're doing this a little bit, just to get the word out, right?
Thank you.
That's sort of why I picked this article. Let's get that discussion going, and we see where it lands. As as a community. So it'll be really cool. So it'll be really fun to see this develop over the next, 4 or 5 years as things move along. So
All right. Well,
very
thanks
cool.
for having me again.
Yeah, Jean-Luc, thank you so much. And that will do, everyone. And I hope this made your Planet Satellite Day just a little bit better. And we'll see you on the next one. Bye-bye.
Bye.